Hello and welcome. My name is Marcos Jorge, and today I will be presenting the paper titled Advanced Bad Data Injection Attack and Its Migration in Cyber Physical Systems. This presentation is for the Intro to Cyber Physical Systems course in fall of 2019. First and foremost, I would like to acknowledge the authors of this paper, Wangping Deng, Ziyu Yan, Peng Zhong, Peidong Zhu, and Bio-Sheng Wang from the College of Computer in the National University of Defense Technology in Changsha, China, and the Institute of System Engineering in the Academy of Military Sciences in Beijing, China. This paper was presented in the MDPI, which is a publisher of scholarly open access journals, and I have also provided a link to the paper in this slide if you wish to take a look. Before getting into the details of the paper, I want to go over some important acronyms that I will be using throughout this presentation. False data injection refers to the injection of bad sensory data to ultimately cause system failure or reduce the performance of the system. A bad data detector is an approach used to detect malicious activity that are performed on cyber-physical systems. Cyber-physical systems will be referred to as CPSs. AFDI stands for Advanced False Data Injection, which will be one of the main topics of this presentation. I will be going over this term in more detail later on in this presentation. Next, we have the outline for this presentation. I will start with a brief introduction and go over some of the main topics that the paper tries to emphasize on. Next, we will depict the AFDI attack, the AFDI attack model, and analyze the limitations of existing detectors for detecting AFDI attacks. Then we will talk about the methodology that the authors use to detect these harmful attacks and also discuss the results and effectiveness of their approach based on a smart grid experiment. We will also discuss some of the work and limitations of those approaches in this space that motivated the authors to develop this methodology to detect advanced false data injection attacks. And ultimately, I will be concluding and wrapping up with some final thoughts on the paper and further work that could be explored. So first, let's start off with explaining what FDI attacks are and what is the main purpose of a false data injection attack. So, what are false data injection attacks? The concept of FDI refers to the action of an attacker compromising sensory data in order to cause inaccurate state estimation. False data injection attacks are becoming more prevalent when dealing with CPSs. So, the authors propose a novel approach on dealing with these attacks and ultimately preventing the attacker's motives. There exist many detection methods today, such as bad data detector, sequence pattern mining, and machine learning methods, which in this paper the authors apply a machine learning technique to their approach called K-nearest neighbor. AFDI attacks refer to attacks where a malicious entity accurately and successfully change sensory data, making the normal system state continuously evaluated as other legal system states. So, in essence, an AFDI attack can lead to an automatic and long-term performance reduction or even cause system failure. So the difference between FDI attacks and AFDI attacks is that AFDI attacks inject legal states in order to cause system failure. In this slide, I have listed the main points that the authors intend to cover in this paper. In this paper, the authors evaluate and analyze the limitations of existing AFDI detectors. They describe common vulnerabilities that you may see in cyber systems today, such as denial of service attacks, and security has been a vital factor for CPSs, and many new vulnerabilities have been exposed. Additionally, they develop an approach using machine learning techniques, specifically k-nearest neighbor technique, to better detect and prevent these type of attacks. Finally, a simulated experiment is provided to demonstrate the impact of AFDI attacks and the effectiveness of the proposed method for detecting these attacks. So next we will dig into the model of cyber physical system used for the demonstration. This model includes three components: the cyber system, which is comprised of the central controller and the state estimator; the communication system, as the name says, this layer is responsible for communicating information between the physical layer and the cyber layer; and finally we have the physical system, which houses the PLCs and sensory data that is sent to the communication system, as you see in the box below. During each cycle, sensors measure the physical process and send sensory data over to the cyber system. The system state is determined by the valuation of the sensory data that is transmitted to the state estimator. In other words, the sensory data will be transmitted to the state estimator, and based on that data, the state estimator evaluates the system state. So if the sensory data is compromised, then the performance of the system may fail. The central controller issues commands to the physical system based on the evaluated state. So when commands reach the physical system, PLCs first receive commands and disaggregate them into many subcommands to control the physical process. This process can be described in the following tuple. C is a finite set of commands from the central controller. T is a finite set of time series. A time series is the measured values of one sensor with the change of time. S refers to a finite set of physical system states. R refers to a finite set of relationships among states and commands. And finally, F is a subset of S. Is a subset of set S. Any state in set F is called an illegal state. So the impact of an attack on the cyber physical system will depend greatly on these three areas that we have listed here: the attack goal, attacker's knowledge, and attack capability. So we will dig in a little deeper on what each of these items are. The attack goal, based on the intent of an attacker, the goal can be divided into two categories. First category would be inject bad data to mask the wrong state. The second category would be inject data to cause an outflow of wrong commands. The authors use the latter for their proposed method. So the attacker's knowledge may differ from system to system, so the authors divide this section into two components, which are perfect knowledge and limited knowledge. In the perfect knowledge case, we assume that the attacker knows everything about the system, from the set of commands down to the illegal states. As for the limited knowledge, we assume that getting information from the public dataset and collecting data by intruding into the CPS can be implemented. The attack capabilities can be three different ones. An attacker can have these different levels of capabilities, and the first one is that attackers can inject any value into any part of sensors. The second one is that attackers can simultaneously modify sensory data of all sensors, but the injected data is limited. And third, attackers can inject any sensory data into any sensor. Now we will be describing the attack model that will be considered for the approach of the authors. So the goal, the AFDI attack goal. So for AFDI attacks, the mismatch of commands is needed in order to affect the physical system. Additionally, continuously masking the fault state is also needed. The AFDI attacker's knowledge: to go undetected for a long time, an attacker should know what sensory data is proper for the current state, which means that knowledge of all of the components are needed. The authors propose a method that attackers without prior knowledge of A, B, and G can perfectly falsify system states. Launching an AFDI attack only requires limited knowledge, so the authors assume that a high-skilled attacker can own the limited knowledge and use this data to generate all the rest of the data to perform a successful attack. The AFDI attack capabilities. So to properly launch an AFDI attack, an attacker needs to have the ability to inject any data into any sensor. In the next couple slides, I will be digging deeper into the approach the authors created to prevent an AFDI attack. The authors set out to create a new detector called Heterogeneous Data Learning Detector, HETED for short. The authors propose an approach that utilizes the popular machine learning technique called k-nearest neighbor and use this in combination with heterogeneous data to prevent these attacks. The proposed method will cover attacks that go undetected for a long period of time and falsifying legal states by injecting legal data into the normal system to cause automatic and long-term harm. The following graph illustrates the HETED detector that the authors created. There are three main components in the detector, which you can see inside the box. There are three components: are process data component, the generate sample component, and the classifier component. Every unit time, HETED receives sensory data from the sensors and commands from the controller. Commands are transmitted to the process data step, and this component modifies these commands as a series of signals and then sends them over to the generate sample component. In the generate sample component, in this step, the signals and measurements of the sensors are combined to obtain a detectable sample, and then it sends it to the classifier component. The classifier stage is responsible for detecting the sample and deciding whether the data is abnormal based on the machine learning technique k-nearest neighbor. So now to go into some detail of each of these components. The process data component changes every command as a control signal into two values, zeros and ones. There are two types of commands: continuous commands and instant commands. Continuous commands represent a command that impacts the system state for some time. Turning a value on or off can be an example of a continuous command. Turning a valve, on or off can be an example of a continuous command. An instant command refers to commands that instantly impact the system. For example, increase commands in the smart grid is a case of an instant command. We will be discussing the concept further in the simulated experiment. This step here is arguably the most important step as it generates the data properly so that the detector can detect the attack. In the generated sample component, the signals and sensory data is combined to generate a sample and then send the sample to the classifier component. The sample is then created using the concept of first difference, which is illustrated in this equation we have here. The variable v sub s at time interval t represents a combination of signals and time series at time t, and in order to capture the temporal structure of data sequence. In the classifier component, labels are annotated on every historical sample. If the sample is normal, the corresponding label is 0. Otherwise, the label is 1, and an alarm is issued from the detector. So the authors ran a simulation to validate the impact of AFDI attacks and evaluate the performance of HATID. The simulation was performed on a smart grid where the imbalance between the demand and generation of electricity can lead to a deviation of the frequency from its normal value. If the deviation is larger than the threshold for a long time, then some generators may be disconnected from the grid, leading to electrical failures. The direct load controller that we have up here is responsible for recovering that deviation in frequency, and this controller is capable of turning on and off electrical appliances to change the loads of the smart grid in order to decrease the deviation in frequency. When the frequency is lower than the normal frequency, which in this case is 50 Hertz, the direct load controller decreases the use of the direct load. Consequently, when the currency frequency is higher than the normal frequency, the direct load controller increases the use of direct load. So in the graph above, we have an example of how the system would perform in a normal setting. For this example, we have two similar situations. Situation 1 shown in the blue line, and situation 2 it's shown in the orange line. In situation 1, the frequency demands increase, and in situation 2, the frequency demands decrease. So at time interval 0, the frequency demands change and the direct load issues command C3 or C6, as you can see here, and thus the frequency becomes stable at 22 seconds. This stabilization of the frequency is the expected behavior, which successfully avoids any electrical appliances being harmed. So now the measurements of demand and frequency under an attack are shown in the graph below. An attacker is able to use measurements of demands and frequency under either situation to replace the measurements of demands and frequency, and then attack may last for up to 100 seconds. So due to false data injection using measurements, the direct load controller thinks that the frequency is lower than the normal frequency, and thus a command to turn off the loads or turn on the loads is executed at 22 seconds. as we can see here. So we can see that the real demand is smaller than the generation, and the operation makes the deviation of frequency larger, as shown in the graph at the bottom right over here. The deviation that occurs between 22 seconds and 100 seconds will cause the generators to be disconnected, and therefore electrical appliances may be broken. So now we will be going over the performance and the final results of Hatid on the smart grid scenario. The authors use false positive ratio and false negative ratio to compare the performance between Hatid and FDML, which is another approach to detect these type of attacks. Both of these detectors were implemented using Python. So the false positive ratio can be referred to as the ratio of samples that are secure and classified as anomalies to all secure samples. False negative ratio, on the other hand, is the ratio of samples that are anomalies but are classified as normal samples to all abnormal samples. The authors launched 50,000 AFDI attacks at different times to obtain 50,000 samples. Every attack lasts about 120 seconds. So 49,000 attack samples and 49,000 normal samples are used as training examples, and the extra 1,000 samples are used for testing samples. In the graphs, we can see that the false positive ratio for Hatid is lower than FDML. We can also see that the false negative ratio of Hatid remains lower than FDML. So comparing the results of the two detection methods in the smart grid simulation, the false positive ratio for Hatid is very small, and it is lower than 20%, which is a good detection effect. The authors explain how there are extensive studies on FDI attacks. However, previous FDI attacks mainly pay attention to masking the wrong system state. That's why the authors used the advanced false data injection approach. They also point out that other studies do not discuss how to keep going undetected for a long time. One of their main pitches is that they continuously falsify legal states by injecting legal data into the normal systems to cause long-term system failure. The authors did a great job of covering all the points in their proposed AFDI detector. Their results showed that their approach is very effective and can significantly improve the detection of these attacks. In the paper, the authors mentioned that they plan to deliver detailed analysis of the convergence of detecting other attacks in real-world applications. I thoroughly enjoyed reading this paper as it was very informative. So now we can conclude this presentation. Thank you for your time.